Hi and welcome back to the Mr. Talk Maths video, and this week's video is trying to find the area of these blue triangles inside of this square. So it is a square. I've labelled all the vertices where the lines are touching the square and the corners of the square and so forth, and also where they're intersecting, because I know that's something that some people mention sometimes, so I've made sure I've done that this time so that people can put down their solutions in the comments. And now this was a little bit of a tricky problem. I mean, maybe a little bit more than a bit of a tricky problem, as you'll see when I'm going through it. At least I found that way anyway. If you had a better solution, a quicker solution, I'll be very interested to see it in the comments below. Now, without any further ado, if you want to have a go at this problem, obviously pause the video and you can have a go at it. Otherwise, I'm going to go through my solution now. So, first thing is labelling some of the sides. So I put on X's here and I put on some extra right angles. The reason why is because then I could start to look at a few things, such as some similar triangles. Now the next obvious thing to me was to work out the length of this side using Pythagoras. So I've got 4.8 and I've got 6, and I don't know the other lengths past that intersection point. But I can use those lengths to work out the length of the side F to C. Now then what I want to do, because there's so many different triangles in here, is to start to label some of the angles. So I label one of them theta, and then obviously the next one in that triangle is going to be 90 minus theta, and then we can work our way around to the next triangle, which is going to have an angle of theta there. And then we have got the other corner of that triangle DGC, or CDG, which is going to be 90 minus theta again. So we've got there two similar triangles. We can then put in, or what I thought, and this was the next bit really, this putting the line in here was quite a tricky bit to kind of figure out, because at this point I tried a few different things and it took a little bit of time to get anywhere. But putting this line in helped because it allowed me to again create another similar triangle. So we've got a right angle at the base of that line where G is, which then means that we're going to have another similar triangle with the top angle being 90 minus theta. So that was quite useful as well, because now I've not got two similar triangles, I've got three. Then what I wanted to do is I wanted to start to see if I could utilize these similar triangles in some way. So labeling some of these sides, A and B, or whatever you want to label them. And then I realized that I could use those similar triangles I mentioned earlier. So I've got DGE, or DEG, depending on which way you want to say it, and CDG. They are similar triangles. So if I bring those outside, and obviously I've rotated them and made them the same orientation here, and you know, reflected them as necessary and things like that, but they are similar triangles. We know that because the angles are the same, and I've labelled them accordingly. So then I looked at it, and well, my scale factor, I've got 6 to A, so, or A to 6 if you're going from the smaller one to the larger one, so that's going to give me a scale factor of 6 over A. Now if I then use that with B, the side EG to DG, it's B times by 6 over A gives me A. That then allows me to write A in terms of B's and A's. So A is equal to B times by 6 over A. And then what I can do, which is quite nice, is I can rearrange it and simplify it so that I get A is equal to the square root of 6b. That's by multiplying both sides by A to get A squared equals 6b, and then square rooting to get A equals 6b. And that then allows me to replace the A on my diagram with root 6b. Okay? Now from there I can find X, because if we look at the triangle at the bottom now, D or CDG, the one that's not blue, the white bottom triangle here, I've got root 6b, I've got 6, and I've got X as the hypotenuse. So if I use Pythagoras again, I can get X is equal to square root of 6 squared plus 6b, because I've squared the root 6b. Okay, now the next thing that I can do is I can write x in terms of b on this right hand side, and then I can start looking at this blue right hand side triangle. I can start looking at the top corner here, which should have been labelled B, but I've somehow lost my label up there for the B. There we go, it's back again. So that top side there, B to F, is going to be the square root of 6 root 41 over 5 squared, which is 1476 over 25, minus square root of 36 plus 6b squared. So I can simplify that a little bit, because I can do my fraction, take away my 36, and then the minus the 6b as well. So I get square root of 576 over 25 minus 6b. Now, this is good because it's getting everything in terms of one variable, b, which is going to be helpful in a second, because when I've got, well, it leaves me only one thing to work out, essentially. So I need some equality somewhere, which we'll see in a second, we'll see very shortly, but reducing the variables in this way is going to be very helpful. Okay, so put that on my diagram and tidy it up a little bit. And then the next bit is a really key bit with this vertical line from F to G. And that is the fact that I have got equal triangles. Triangle CDE is equal to triangle DGF. Now that's because they're similar triangles anyway, because the angles are all the same, but they're not only similar triangles, they've got a corresponding side that is equal. So G to F is equal to D to C, because G to F is the height of the square and D to C is the side of the square. And so because they're similar, i.e. all the same angles, which means there's a scale factor between them, and one of the corresponding sides is equal, the scale factor is 1, the triangles are equal. Now that is the key bit, because then that allows you to equate sides. And so then you can get that the side D to F, which is 4.8 plus root 6b, is equal to side C to E, which is 6 plus b. Now, when you rearrange that, what you get is a quadratic in terms of root b, because b is root b squared, and then we've got root b, and then we've got a constant term. So what you can do then is use your quadratic formula with 1 minus root 6 and 1.2, but what our solution will give us is root b. It's not going to give us a solution for b because our quadratic is in terms of root b. That's fine, because then all we've got to do is we've got to square both of those, and we get 9 plus or minus 3 root 5 over 5. Now again, I'll tidy that up and clear a bit of space. Okay, so we've got values for b, we've got 2 of them, and actually we can't rule either of those out at the moment because neither of them are negative. One is about, well, one's less than 1, but it's still positive, so you know we can't rule it out, and the other one is, you know, slightly bigger, but again still positive. So once we've got everything in terms of b, we've now got the full width of the square in terms of b, we've got the areas of each triangle that we can work out in terms of b, we can start working things out. So the area of triangle DEG is a half of b times by root 6b. And then the formula for the area of the right hand side triangle, triangle BCF, is equal to a half of square root 576 over 25 minus 6b times by 36 plus 6b, all square rooted. Now I've put that all in one square root because if you times square root of something times by square root of something else, that's the same as the two things times together inside of the square root. Okay, now the formula for the total area is those two things added together, and they've both got a factor of a half, so I've pulled that out the front, and then I have put the b inside the root. So to put that back inside, I've got to square it, so I get b squared inside 6b times b squared is 6b cubed. Right, so now I'm just going to put my values for b into this formula, and the reason I wanted to get this formula is because I can just use the answer button on my calculator and just type in 9 plus 3 root 5 over 5 equals, got that as my answer button, and then I can put that as answer in this formula in my calculator. And so it just makes sure that there's no rounding errors there. And so the final answer, and you get the final answer depending on whether you put either of these two things in. So you can put 9 plus or 9 minus 3 root 5 over 5 in as b, and you get exactly the same answer, which is a bit weird, to be honest. And it gives you quite an odd answer, I think, as well, because it doesn't give you a surd. It gives you 14.4 centimeters squared. How cool is that? So, I hope you enjoyed that problem. Like I said at the start of the video, if you could find a more straightforward way, a more succinct way of working that out, I'd be very interested to see it. And thank you for watching. I want to say as well, thank you for the subscribers, because we're up to 700, just over 700 subscribers now, which is amazing to me, to be honest, in, less than a year, really, because I started doing this one a week the end of, or the start of September last year. So, that's really incredible. And, I feel quite honoured, to be honest, that, people are enjoying these videos and are watching them. And the final thing from me is that it is my birthday the day before this video comes out, so on the Sunday. So, if you want to, you can say happy birthday down in the comments. I would very much appreciate that. And as always, like and subscribe, because that does me a favour. I really appreciate that. Okay, I hope you've enjoyed, can't get my words out. Hope you've enjoyed the video, and have a great week. I will see you next week for another one. Bye-bye. If you like this video, then there should be plenty more videos just up here. Hopefully it's here. That's where it should be, the one that you want to watch next. Okay, see you in the next one. Bye-bye.